Good morning, everyone. Today we're looking at mole calculations, and as I promised last week, we are going to look at questions where you've got two equations that are involved. Now, first off, why would I need a second reaction? Now, if you look at this, there's a reaction with an acid, but the magnesium oxide over here is not in solution, it's insoluble. So this is a solid. So here you can't do a titration, right? And then if they ask me the mass of this magnesium oxide, I can react that with hydrochloric acid where I know the concentration. But the problem is I don't know when to stop adding, when I am in the ratio 1 to 2. So what we're going to do is I'm going to add the HCl until I've got a volume that is in excess, so that there is more than enough to react with all the magnesium. And then I can do a titration with that HCl to determine how much extra I've put in. So the sodium hydroxide react with, and that will give sodium chloride and H2O. And now the trick is to remember whatever moles were in excess there will be the moles that will react in this one. Right. Now, to do this, you really need to remember if something is in excess, it means there's something left over. And immediately it is difficult to keep your thoughts together about what do I have, what reacted. And so I always say, if you've got an excess, immediately go and for yourself draw a table that keeps all the information together. So I always draw a table that is the moles that I put in, and then the moles that react, and then the moles that are in excess. Right, and then obviously whatever is in excess over there will be the moles that is used in the next one. Right, so when you are looking at that, the moles that are in excess over there will everyone be used over here usually, right? But just check with your question. Sometimes they only take a specific amount of that. Instead of, say, they had 250 cube centimeters reacting, they can say, okay, let's only take 25, right? So just check, but usually the number of moles in excess over there are also the number of moles that will react in this one. So what they do usually is they give you the volume and the concentration that they put into the reaction, and they give you the concentration of the volume that is needed to neutralize that excess. Right. So what we're actually looking for is we're looking for the mass of magnesium oxide, and we'll get that from the moles. Right. So first I'm going to work out how many moles, and now I have to remember it's not the moles that I put in that will tell me how many magnesium oxide moles reacted. It will be the hydrogen chloride that reacted that will tell me how much magnesium oxide reacted. So what I'm going to do is I'm going to work out with the concentration and volume the moles that I put in. Then from the titration we will get the moles that were in excess in that reaction. And then I will use that moles that we put in and the moles that's in excess, that's left over afterwards, that remain, and then I will subtract them to know how many moles reacted. Right, and that will give me the HCl reacted, and that will give me magnesium oxide reacted, and I can use that to get the mass of the oxide. So guys, there's a lot of parts to this question. So first off, I will work out what is the number of moles that are put into this, the reaction. And then we have to work out how many moles of sodium hydroxide were used to neutralize the acid that is in excess. And then once we've got that ratio 1 to 1 in which they react, because it's a neutralization, right? So 1 to 1 ratio, and that is going to tell me how many moles of HCl reacted over here and was in excess over there. And then together with what I put in, subtracting from what I've got left over will tell me what reacted, and then with the ratio that will tell me how many moles of magnesium oxide reacted, and that will give me the mass. So if you look at this, 1, 2, 3, 4, 5, 6, 7 different steps in this. Now, if you do this, if you draw a neat diagram showing what information do I have and what can I do with that, it actually gives you a sort of a roadmap for traveling. And then if someone up there in front drops his pencil case and everyone's looked up and looked down, you won't have lost your way because you will immediately know where you are and what you are doing. Now let's try to apply this. Now the first question I want to look at is last year, 2019, at the final exam, chemistry exam, right? So here they say a hydrogen bromide solution reacts with water according to the following balanced chemical equation. Yes, it's an acid, so I expect ionization, and it gives me hydronium ions, right? And then they give you something new. They tell you that the Ka value over there is 1 times 10 to the 9th, which is a very big number. And remember, Ka is like Kc. It is the products divided by reactants. So if you've got a very big Ka value, that tells you I've got a lot of products compared to the reactants. So most of the chemicals are actually in the product stage. So here that will tell me it's formed a lot of ions. It's ionized almost completely. So this is immediately a strong acid. So it's not one of the few that were prescribed for us. We didn't learn that. But from that Ka value, you can deduce that HBr, hydrogen bromide, is a strong acid. Right, we're not going to look at 7.2. We're moving on because we actually want to look at 7.3. Now here they tell you that HBr reacts with zinc hydroxide according to the following equation. And once again, you'll see that is a solid. That's why this can't be a titration, right? An unknown quantity of zinc hydroxide is reacted with 90 cube centimeters of HBr. So there they give you the volume of HBr that they put in a flask. Assume that the volume of the solution does not change during the reaction. Now, why would it change? Because we are producing water molecules, but there are so few compared to the solvent that we can actually ignore that. It does not change much. Right, and then they give us that word that's giving everything away, the excess, right? So the HBr is in excess, and immediately I know how I'm going to start this question. The excess is neutralized by 16,5 cube centimeters. So there they give me a volume of NaOH of concentration. So there they give me a concentration and the balanced second equation. So we've got two equations and they tell us HBr in excess. So immediately I'm going to say, okay, for the HBr, I'm going to have a table to show me how many moles I put in, how many moles reacted, and how many moles there were in excess. And remember, that excess moles will be the ones reacting in the next equation. Right, now, what do they tell you? They tell you they are putting in 90 cube centimeters of HBr. So over there, what they're putting in, they're giving us a velocity of 90 cube centimeters. They're not giving us the concentration, right? And then they tell us that excess is neutralized, completely reacting with NaOH of a volume of 16,5 cube centimeters and a concentration of 0,5 moles per cube decimeter. Right. Now, the moment I see that, I'm immediately going to say, okay, so that's going to give me that moles, and that moles can give me that moles, because I know the ratio over here is 1 to 1, right? neutralized, they are in the right ratio 1 to 1. And that is going to give me that excess over there. Now, what do they ask? First off, they're asking, what is the pH of the HBr solution remaining in the flask after the reaction? So after the reaction, when you have that excess, there they're asking us, what is the pH? Right. And then the second question, they are asking us, calculate the mass of zinc hydroxide that was initially present in the flask, okay, initially. So they are actually asking what's the mass over there, right? Remember, I will get there via the moles. And they tell you if the initial concentration of the HBr was, and there they give us concentration 0,45 moles per cubed decimeter. So in the first question, they're asking us pH there at the end. Now, there's always more than one way, or often more than one way to do this. And one way would be to use the titration equation, right? Na over Nb, Cava over Cbvb, right? Use that to get the concentration of the HBr and then say, but that is also the concentration over there, and use it for the pH. So that is maybe the shorter route, right, for the first question. But I know I eventually want to get that mass in the second question. So I'm going to do maybe a little bit longer one first, so that I have the answer of moles that I can use in the second part, right? But for marks, it doesn't matter what you do. So for 7.3.1, I'm looking for that pH. I'm going to start over here, and I will say C equals N over V. I'm working with the NaOH. Right, what do I know? Concentration 0,5, and the volume, I've got it in cubed centimeters, so I will divide by 1,000 so that I end up with cubed decimeters. And once I've got that, then I can work out the moles, and that is 0,00825 moles, and that is now of NaOH. Right, so I've done this. Now I can use that to calculate the number of moles of HBr. What do I know? HBr always reacts with NaOH in the ratio 1 to 1. So if I've got 0,00825 moles of NaOH reacting, it means it reacted with 0,00825 moles of HCl. Now that means I've got that many moles of HCl that reacted in the second reaction, right, over there. But that immediately tells me that number of moles were in excess in the first reaction. Right. So now I have moles, but what am I actually looking for? I'm looking for pH, and to have pH, I need hydronium ions. Right, I know the concentration of hydronium ions, but we don't have hydroniums, we have HBr, we still have the acid. But first, I will try to get the concentration of that acid. So concentration is moles per volume. And how many moles do I have? Now remember, we are working with this excess. We're working after the reaction, after the first reaction. So after the first reaction, we know that the HBr, just remove that a little bit, that is in excess, that's left over after the first one is 0,00825. Right, so I've got 0,00825. Volume, well, this is a solid, no volume. That one, they already told us we put in 90 cube centimeters. And then in the question, they also told us that the volume does not change. So that water that was produced was a very small amount compared to the volume of the solution. So here I will just have that 90 cube centimeters. So that's 0,09. And if you do that, you end up with 0,092, and that is now moles per cubed decimeter. Now, I work with the moles of HBr, so what I actually get here is the concentration of HBr. But to go to pH, I need to go from the acid to the hydronium ion. And first off, I will say HBr. What do I know about HBr? Well, they were very nice with us that in the very first question, they showed us that HBr is a strong acid. And that immediately tells me it will ionize completely. Right, it ionizes completely. So every single molecule of that 0,092 in every liter will ionize. And since it is a monoprotic acid, it means for every one HBr molecule that react, I will end up with one hydronium ion. Right, and that is important to show that because it could have been two for something like sulfuric acid. And that immediately tells me my H3O plus concentration is therefore also 0,092 moles in every liter per cube decimeter. And then it's very easy to get the pH. So for pH, it's just negative the log of that H3O plus concentration. And don't get lazy, guys. Some of you will immediately substitute in, and then you might lose that mark. So remember, you have to have an equation, then a substitution, and then the answer. Right, so for the first one, that was the pH of that final solution. Right, next we are asked to work out that mass. So now I've already worked out that excess down there. Let's write it down there, 0,00825 moles is in excess, right? Now I need to know how many moles were put into the solution. Right, so let's start over there and say, okay, I'm working with C equals N over V. I have a concentration of 0.45 and the volume over there was 0,09. And that tells me moles over there, 0,0405 moles, and that is now of the HBr that I've put into the reaction. Okay, so I've got that one. Now, what am I going to do? I'm going to use the moles that I added in the beginning and subtract the moles that were left over, the ones that were in excess, to get the number of moles that react. Right, so the number of moles that react is 0,0405. We've calculated that. That is what I put in, minus what is left, what is in excess. 0,00825 is left over afterwards. Right, and if you subtract that, you will end up with 0,03225 moles of HBr that are reacting over there. And that is going to tell me when I use the ratio 1 to 2, 1 to 2, it's going to tell me how many moles of zinc hydroxide is reacting. Right, so zinc hydroxide always react with HBr in the ratio 1 mole of zinc hydroxide for every 2 moles of HBr. And now I don't know the zinc hydroxide, but I know the HBr is 0,03225 moles, and it's just divided by 2, so the number of moles of zinc hydroxide is going to be 0,01611 mole. Right. So now I know how many moles of zinc hydroxide, and I just need to take that to mass. So moles is mass divided by molar mass, 0,01611, right? And the molar mass, I'm looking at 1 zinc, 2 oxygen, and 2 hydrogen, and add them all together, you will end up with 99. And that tells me the mass is going to be 1,595 grams. Now, if you want to, you may have rounded that off to 1,60, but be very careful to have that 0 there, otherwise you won't get this mark, because you need 2 places after the comma. Right. The instructions at the beginning of your exam papers are very clear. A minimum of 2. You can have more, but you may not have less. So definitely put that 0 over there. Right, the next one we are going to look at was a preparatory exam 2019, and that was the one of the Northern PEP. Right, now, first off, they ask the definition. We're not going to look at that, and also calculating the pH of the sodium hydroxide solution. We're not going to look at that. We are going to look at 7.3. Now, they tell you seashells contain calcium carbonate. So if you think about a seashell, part of that shell is actually calcium carbonate. So the shell is the whole thing, but only part of that will be calcium carbonate, right? There's other stuff in there as well. In a test to find out the percentage calcium carbonate present in the shell, 75 cube centimeters, so that's a volume, and a 0.5 moles per cube decimeter hydrochloric acid solution is added to 5 grams of not calcium carbonate, but 5 grams of shell. So I expect there's less calcium carbonate than 5 grams. So don't use the 5 for calcium carbonate. Calcium carbonate is only a part of the shell. Right, and then they do that reaction, and then they tell you the excess acid. And immediately, if I see that word excess, I will know how to approach this. So the excess is then required to react with 20 cube centimeters. So there they're giving me the volume of that and of the above sodium. So there they already gave us the concentration. So we've got concentration and volume. And they're asking us for the percentage calcium carbonate in the seashells. Now think about percentage calcium carbonate. What I need is the mass that is really calcium carbonate out of the possible mass that is all the shell, right? The whole sample that I'm using, right, times 100. So I'm using a sample of 5 grams. And what I need now from this experiment is to determine what is the mass of calcium carbonate that is reacting. Right, now to do that, I am going to look at, well, I'm going to approach this by once again drawing a table for the one that is in excess. Now the HCl is in excess, so I'm immediately going to say I have to be aware that the number of moles that I put in is not the number of moles that react, and it is not the number of moles that remain afterwards in excess. Right, so let's read again. Now what they tell you is seashells containing reacts with, and there they tell me what they put in. They put in there a volume of 75 cube centimeters and a concentration of 0.5 moles per cube decimeter. And then they tell me 5 grams of sample. Okay, I've already talked about that. And now they say the excess is written. Okay, so let's talk about the excess. The excess there will be used in the titration, right? And that excess requires 20 cube centimeters of that solution. So a volume of 22 cube centimeters and a concentration of 0.75 moles per cube decimeter. Right, and what am I actually looking for? I'm looking for the mass of the calcium carbonate. So therefore, the calcium carbonate, I need the mass, which means I will have to work out the moles first. And remember, the moles of calcium carbonate will be given by the moles that react. Not what I put in, not what's left over afterwards, but whatever react will tell me how much calcium carbonate moles reacted over there. So for this one, that will give me moles, that will give me moles, and now I've got a lot of calculations to do, but I've done my planning. So let's start by working out how many moles of HCl I am putting in there. Right, so I'm going to start by working that out. I'm working out C equals N over V. I've got a concentration over there of 0.5. is the moles divided by 75 cubed centimeters will be 0,075 cubed decimeters, and that will give me a mole of 0,0375 moles, and I've worked out the HCl that I put in. Right, so that's the HCl that I put in to the reaction. Right, next up, I'm going to start by looking at the titration down there. Right, so for the titration, C equals N over V. Concentration down there, 0,75. Volume, remember to convert 022, right, to cube decimeters, and then that gives me a concentration of 0,016, concentration, a mole of 0,0165 moles, and now that is for NaOH. And remember to write down what you are working with for you and also for the person who's marking your paper. Right, so now I know how many moles of sodium hydroxide were used to neutralize the HCl. And I know HCl to NaOH, they reacted in the ratio 1 mole to 1 mole. So if I needed 0,0165 of that, it means my HCl mole will also be 0,0165 moles. Right. Now, what's important? It means that is what reacted in the second, right? React in the second reaction. But what I know is if that is what reacted in the second one, only the excess reacted over there. So that also means that was what was in excess, right? That were in excess in the first reaction. So now I know over there that was 0,0165 moles. Right. And what I put in was over there 0,0375 moles. And now I'm going to use this to determine how many moles reacted. Right, so I'm going to use those, and I'm going to say the mole reacted of the HCl will be what I put in, and I put in 0,0375 minus what remained at the end, the excess, and that was 0,0165 that was in excess, right, and it remained. Okay, and if you do that, you end up with 0,021 moles of HCl that reacted. Now, if you know how many moles of HCl reacted, you can use that in our ratio 1 to 2 because I know one of these will always react with two of those. So I'm going from calcium carbonate to HCl. I know 1 mole of this will always react with 2 moles of that. And how many moles will react with 0,021? It's just dividing by 2, so the moles of calcium carbonate over there is going to be 0,0105 moles. And that is what is reacting, right? And then we can work out the mass. So I just need to convert moles to mass. So moles to mass, that will be N equals M divided by big M, 0,0105. Looking for the mass, we're working with calcium carbonate, so it's 40 and 12 and 3 times 16, giving us 100. And that means the mass is 1,05 grams. So in that 5 grams that we started with, 1,05 grams were really calcium carbonate. So 1,05 grams out of the total of 5 gram shell sample that we used were really calcium carbonate. And if you work that out, you end up with 21. But guys, you need 2 places after the comma. So don't skip that, comma 00. Even if your calculator just tell you 21, then you need to have the 2 extra zeros. Right, So guys, this is when you have anything in excess, right? Keep book of what you put in, what reacted, and what remained, what were in excess afterwards. So if you are able to draw or to write down your information in a way that makes sense for you, that will make it a lot easier, because all the separate calculations are very easy. It's just to understand the bigger picture and the context. Right, next week we're looking at moles once again, but we will be looking at things like something that is in excess, and you've got a limiting agent and working pH. And also I'm waiting for more questions from you to discuss in that class. So remember to send us your questions. You can send it to junior.tikkie@up.ac.za.